Hi, John. How are you?
I am well. How are you doing?
I'm very well too. Thank you so much for coming.
Yeah.
We still have a few minutes, so you can still relax and. But in the meantime, I'll put up the link. You can, if you would like, you can try to see if you can click on it. The presentation is so pretty. It's so beautiful.
Okay, let me see. Oh, okay.
There.
Yeah, okay.
Perfect.
Great.
Let's. Yeah, in the meantime, I'm going to share on Twitter that it's about to start. And yeah, I hope you're enjoying your Friday. Happy Friday.
Well, the weather here is beautiful in Rochester, so it's
Oh,
nice.
yeah. Yeah, here too. It was chilly the last days, but today it's nicer.
Yeah.
The fall is the best season, right? Here in New York, since I moved to.
Yeah, especially in upstate New York, the fall I think is really nice.
Yeah, I agree. In Portugal, the fall, and then Germany, where I grew up. I'm originally from Portugal, and I grew up in Germany most of the time. The fall is horrible. It's just rain and clouds and gray, and
Yeah, yeah.
yeah, especially November is horrible. Like it's really horrible. Well, in Portugal, September is still fine. You have the wine grape season, so if you go out to the wineries, you can see the grape getting picked and stuff like that. So that's nice, and figs and so on. But after that, just rain.
Have you spent any time in Brazil?
No, I haven't. I have actually further away family from Brazil, but I've never been. No. Where did you go in Brazil? Like,
Well, I started in Brasilia, but we covered about 1,200 kilometers, so we were all kind of in central Brazil. But I had not realized how prevalent Portuguese is, and in fact, how if I had done a little research on this, perhaps I would have figured that out. But I was with colleagues, so that was fine. But I think the number of places I went and visited that people only spoke Portuguese was surprising to me. So I just didn't realize that was the dominant language there. So in such a large area, but it was.
yeah, it's it was well, it's not like it was taken over, but it was then the first colony that became independent without any violence because it was the son of the king that kind of was rebellious and then just declared, I don't want to be ruled by my father anymore. And then it was the father didn't want to kill the son. If
Mm.
that's true, I don't know. History is always just written by the people that win. So if that's totally true, I'm not sure, but that's the story, I think, as far as I know. So
Well,
yeah, then they became
close.
independent, but slavery was only abolished very late. It was the last of the ex-Portuguese regions that abolished slavery. Like they were very, yeah,
Mm.
they were very stuck on that. But other than that, I think it's a beautiful country. It's just right now the political.
Yeah, yeah. It's very. It was good to do field work there before the elections. Let's put it that
Yeah.
way.
Yeah, it's very difficult. It's such a variety and huge country and variety of people with different ethnic backgrounds and religious backgrounds. It's
Yeah, yeah, yeah.
yeah. but it's supposed to be beautiful. My mom went a few times, but I've never been.
Yeah, I really enjoyed it. The people were great, and it was good for my work, and it was a great trip.
Did you ever go for carnival season?
No, 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 I haven't gone for any kind of touristy things, but I was definitely an accidental tourist in many ways, just visiting different areas. But like I said, we covered a kind of a large area in central Brazil. But yeah, there's plenty of places we didn't see. Yeah. I'll have
Yeah,
to go back.
yeah, for sure. And you went also, yeah, you went to all kinds of places. But where did you go again in Africa?
I
Was
was
it?
in Namibia in July, and yeah, I've done a lot of work in South Africa and Zimbabwe, Botswana, but this most recent trip was in Namibia.
Yeah, it's also supposed to be very beautiful.
Yeah, yeah, it is. So, you know, the Namibian geology has a lot of similarities with that of Brazil, because you know, once the oceans were before the present day Atlantic formed, they were adjoined. So that's why we have these similarities in geology.
I don't know if you. It's a long time ago, but that I heard this, but I wasn't sure if I really heard this right or not. That the Nile is basically how it's currently right now. That it's kind of the climate is feeding the Amazon from the Nile, basically. Is that true? But now with climate change, it could get kind of reversed, and there will be more rainfall again in some parts of Africa, but not so much in South America again. But because of the current changes, I'm not sure if it's really true. I think I heard it or read it.
Yeah,
It's
it's
probably
actually
ridiculous.
it's a difficult question to answer because it there are many variables involved. The and you really need to get down to the level of specificity of a different of a specific area, because some areas will be expected to have more rainfall and some areas will be expected to have less. But all of this is predicated on predictions on what's going to happen to ocean currents and temperature at that time. And if those change, then many of those subsequent predictions are somewhat questionable because they will affect the kind of latitudinal temperature gradients. So, you know, I'm reluctant to talk about these things without a particular model in front of me, to talk about the specific predictions of those models and you know, what could actually happen. So I think we have to be careful about generalities like that. But there are some models that do, you know, predict some things like that you are talking about.
Okay. Yeah, I imagined that it was oversimplified.
Yeah.
Yeah, almost. We can almost start. People will start coming in. I'm sorry, I got a little bit sick overnight. I don't know. But um, people will continue coming in, but we can start slowly with introduction in a minute, and with interview questions, and then we'll go from there. Hey everyone, thank you for coming. Feel free to share the room with people you think that might be interested in this topic. Um, the presentation is pinned on top of the room, and we're going to start. Oh, actually, now it's already time. Um, yeah, so welcome everyone to Science Society, and of course, a special welcome to Professor John Tarduno here. And before we start going into the topic, let me give you an introduction about John, so you get to know him a little bit better. Professor Tarduno, he's at the University of Rochester, and he received his bachelor in geophysics from Lay University and his master's and PhD in geophysics at Stanford University. He was a joint Oceanographic Institutions Fellow at Stanford and NSF postdoctoral fellow at the ETH Zurich. And then he was an assistant research geophysicist with Scripps Institution of Oceanography. And then he joined in 1993 the University of Rochester. And there he served as a chair of Earth and Environmental Sciences. And he was named the William R. Keenan Jr. Professor. And since 2019, he has served as the Dean of Research of Arts, Sciences, and Engineering. Professor Tarduno also founded the Rochester Paleomagnetism Laboratory, where he and his group developed methods to recover past field data from single crystals. And his group uses ultra-sensitive magnetometers to read this magnetic history. He sailed on many ocean drilling cruises, and he did he conducted a lot of field work, also with students in India, Lesotho, Swaziland, South Africa, Botswana, Zimbabwe, Australia, New Zealand, Brazil, and led expeditions in the Sahara, and even 10 to the high Canadian Arctic. He has over 100 of publications in very high impact journals, and he also received a lot of prestigious awards, and just to mention like a couple of them, he was named in 2006 the Guggenheim Fellow, and he was awarded the Prize Medal of the Royal Astronomical Society for his achievement in detecting the absolute motion of hot spots, overturning the notion that they are fixed points over which the tectonic plate move. This opened the way to new insights into mantle convection. And in 2017, he received the EGU Petrus Peregrinus Medal for his seminal studies on the evolution of the Earth's magnetic field. And one of his articles had like over 800,000 reads. That I posted it in the chat, this article. And he has been also featured in recent BBC Science Channel documentaries on the subject. So it's such an honor having you here, Professor, and we are really, really happy that you took the time out of your busy schedule to come here and make this beautiful presentation. But before we start, if that's okay, we usually ask a couple of interview questions.
Yeah, sure, great. Thanks. Thank you very much for the introduction.
How, if you can remember in your life, how did you end up choosing a path of becoming a scientist? Was it something you always wanted to do? Was it maybe a teacher, a class, or a book that kind of sparked your interest in going and choosing this life?
Yeah, so I would say that growing up, I always had an interest in, I think, things outdoors and natural science in general. I can't say where that came from because I think it's just something that always interested me. But I think I had several very good science teachers. I think in grade school, secondary school, that really laid an important part of that foundation. But I think it wasn't really until college that I knew that I could combine many of the things that interests that I had, which I at that time considered to be more like hobbies, that I could actually think about doing that as a livelihood. So it was really, I think, in college where I met a couple of professors who were deeply interested in geophysics that really kind of cemented that foundation.
Yeah, that's interesting. That you, yeah, that you don't, yeah, that you see basically that you went, yeah, with your curiosity, and um, I think that's a wonderful life to spend. For a wonderful way to spend your life, I guess.
Mhm.
And how did you become interested in this field of research? And I know that this work has been an ongoing path of yours. Like, yeah, is there maybe a story about how you began to be interested in this and to research it?
Yeah, um, I think one of the foundational moments for me, kind of going back to before this actual topic that I'm going to speak on, really again was in my bachelor studies, and at that time I was just learning about geophysics, and I was attending sort of an informal seminar that some professors were having with graduate students, and we were talking about these things very late into the night. And I was, as a young person, I was kind of amazed that here we were talking about this completely basic research academic topic. And there were people who were much older than me. They had families and they obviously had other things to do, but this was so intrinsically interesting to them that they were just there, and they were talking and arguing about these things late into the night, and I and that was fascinating to me that people would be able to kind of devote their lives to that kind of pursuit of knowledge. So I think what I've tried to do a lot in our research and in many of the things that we do in my group in my lab is kind of building upon that experience is we try to provide opportunities for discovery. I mean, I think discovery can take place in many different ways. It can take place when you're doing field work, and can take place when you're doing laboratory work. It can take place when you're writing a paper, and you just haven't really thought about the results yet. And I think that's really important. And much of what I'm going to talk about today really did start with a discovery that we had in our laboratory.
Well, that's yeah, I enjoy those type of conversations that go on, outside of the lab. I was at the marine biological laboratory um, for a few summers and 1 year round, and the atmosphere is kind of like that there. We have like late night lectures, but also like with wine and some
Yep.
food. Yeah, I think. Do you think that still, um, that happens still a lot, or is it kind of more like a Is it nowadays more like a regular job, like being in a company? I feel that switches a little bit.
I think
Um,
it depends on where you are, and I think that yeah, there are places perhaps that are more corporate like, and I think those people are unfortunate because they're missing out. But yeah, I think it's really up to people like myself and who form research groups to kind of keep that alive and to really kind of create this kind of feeling of both kind of local and kind of larger communities. Um, but really, again, kind of um, making particularly students feel that they're part of the process, and they can make discoveries as much as any experienced person. It's just kind of gaining the skill set, and just keeping the curiosity channeled in sort of very productive ways.
Yeah, well, yeah, they're lucky to have you as a professor, and yeah, I agree. That's really important, because it is a different life than just a regular job. You don't really go home and you stop thinking about things. So. And if you, yeah, so there has to be kind of a community, making sure you're not the only one like that. So, no, but yeah. So the presentation for everyone is pinned on top of the room, so everyone can access it. And yeah, the stage is yours. Thank you so much.
Okay, great, thanks. So the first slide is just one of introduction, and so we'll move past that pretty quickly into the second slide. And really, the second slide illustrates what my group has been working on, particularly focused on for the last 20 years. And what this shows is this balance between the sun, and this is not to scale, by the way. It's a picture of the sun on the left and Earth and what we call the magnetosphere surrounding it, this cocoon that is created by Earth's magnetic field. So the point of this picture is really to emphasize that um, out in space today, we have a pressure balance. So we have particles that are constantly streaming from the sun, and there's a balance between those and Earth's magnetic field. Earth's magnetic field, we say, stands off those charged particles from reaching Earth's atmosphere in particular. Now, you may, all of this is largely invisible to you, except that you may occasionally hear of times when you see auroras, for example, at low latitudes. And what's happening there is there's a particular event that comes from the sun, something we call a coronal mass ejection, where there's a much larger mass that is thrown toward Earth. And at that point, we can actually charge up the magnetosphere and we can then see effects of this. But most often, we don't see this effect at all because that point, that pressure balance, is very far from Earth. It's something we measure in Earth radii. It's over 10 Earth radii from Earth. But what we've been trying to do in our group is really trace that back in time. Was it always really so far from Earth, or was it actually much closer? And one of the reasons we want to understand that is kind of shown in the next slide, number 3. And it goes to the larger question of why did Earth retain its water? Of course, we think about Earth as the water planet, but what would have happened if we didn't have a magnetic field? And we'll return to this at the end of the presentation. The principal thing and the importance about the Earth's magnetic field is it really protects us from these charged particles, which can erode the atmosphere. If they were not present, if the Earth's magnetic field had not been present, it could erode the atmosphere. And once the atmosphere starts to be eroded, it can take away the water also. So the real question is, why did Earth retain its water and evolve as this habitable planet with sustained habitability that we know about it? and what role did the Earth's magnetic field play in that. So that's a general theme that we'll be looking at. The fourth slide gets a little bit more to the topic of our most recent publication, and something about the internal structure of the Earth. Now, I think many people may be aware that the Earth has a core. This core, which can most easily be seen in the inner layer at the figure on the far left, is made of liquid iron. And that liquid iron is swirling around and convecting, and that's the source of the Earth's magnetic field. But within that liquid iron is actually another layer. So if we jump all the way to the right one actually shows all the layers that we have today in the Earth. I'm not talking about the uppermost parts of the Earth, the Earth's crust and lithosphere, but we're going to go beneath that for what's labeled an A. That's Earth's mantle, so that's solid rock. But then B is the start of the core, and that's the liquid, now what we say outer core. But within this outer core is a solid inner core. That's C and D. And that actually has two different parts. They're both solid, but they have slightly different compositions to them. And what the figures show from left to right is this realization of the community that the Earth did not always have a solid inner core, that has actually grown through time. And what we're trying to do is to determine some of the temporal characteristics of that. It started out with a small seed, like the one in the center, and then it grew this what we call outermost inner core. And when did that actually happen? And how did it happen? Why did it happen? Those are the kinds of things that we're interested in. And finally, the thing I want to remind you about here is that convection in the liquid core is needed to produce the magnetic field. So we have to have the liquid iron twisting around, and when it does that, it twists around the magnetic field lines in the core, and that's really important for generating the magnetic field and sustaining the magnetic field. Now, to do that, we have to have an energy source. The most typical energy source is that we remove heat from the core. We move heat and we transfer it to the mantle. There can be some chemical processes that produce this separately, but that's one of the main ways of actually producing the magnetic field. The other way to do that is just purely by the actual crystallization of the inner core. When that iron actually starts to form this kind of solid form within the very center of the Earth, that releases heat and we say causes buoyancy, and that can also produce the magnetic field. So it's actually very interesting that today what's actually producing the Earth's magnetic field is mainly due to this crystallization of the solid inner core. But very early in Earth history, the Earth's magnetic field, if it existed, had to be generated. Its power source had to be formed by something else, and we'll get to that in a second. Now, number 5 basically just is a very brief review of how we approach the problem, and particularly focusing on one aspect of our analyses. We kind of roam the globe looking for the best magnetic recorders, because you can think about magnetic recorders. Natural rock magnetic recorders are in rocks, but these rocks have different magnetic minerals, and some of them are really good magnetic recorders, and some of them, or most of them, are really poor magnetic recorders. So what we have found is that certain crystals within rock, within those crystals, and those crystals that are shown in A and B, are only about 1 millimeter in size. Within those crystals, certain crystals have magnetic inclusions, and those are shown in C and D. And the scale bar now there is 200 nanometers. So these are really tiny magnetic particles, and you'll see they're needle-like forms. Well, those needle-like forms turn out to be perfect magnetic recorders. That is, when they form, they can lock in a record of the Earth's magnetic field. And the important part is that they're not going to change their magnetization. So we spend a lot of time trying to find those rocks that have those crystals to be able to get good recordings of the Earth's magnetic field. And if we jump to number 6, we've developed a whole series of techniques and equipment. This is currently the most sensitive, we say, 3-component magnetometer. It's something called a superconducting quantum interference device magnetometer. It's operating at cryogenic temperatures. And it enables us to measure these very small particles with great accuracy. And this was developmental work in our laboratory together with industry. And we use things like CO2 lasers to heat the samples to be able to recover these type of magnetizations that they hold. Okay, number 7. We're going to run through the history, in our view, of the Earth's magnetic field, starting back from the oldest records, which we think are around 4.2 billion years old, all the way to present. So what the vertical axis shows is the strength of the Earth's magnetic field, and time is running along the x-axis. So, and the present day field value is in the pink line. Together, the blue field is the current range of the present day magnetic field. So the first takeaway of this is that we think that the Earth's magnetic field is really old, and we think it actually is nearly as old as the Earth, or at least the Earth after we say the giant impact that formed the moon. As soon as the Earth cooled from that, probably 100 million years or so, it's possible that we had a magnetic field being generated. So what we think, though, is that that early magnetic field, if we just jump to the next slide, was generated probably by processes that aren't occurring today. There were probably some minerals that were exolved or dissolved, we could just say, within the this very hot initial core of the Earth, and that core would have been present when the moon formed. And that those materials kind of solidified, and that produced some energy to drive the Earth's magnetic field. But that kind of dissipated quite quickly within the first couple 100 million years. And that's that kind of pink arrow that's kind of trending downward. But then the field intensity increased, and we think, if we go to the next slide, that was probably the transition to a mantle, and then hence the core being cooled by plate tectonics. So if we just jump to the next slide, number 10, today when we think about the Earth's surface, we have roughly 12 plates that are covering the Earth's surface, separated by either ridges that can form new ocean basins, the red lines in this plot, and subduction zones where oceanic plates are diving underneath continental plates. That process is actually really efficient of removing heat from the Earth, particularly for cooling the mantle. Now, if you go back to what I started with, that we have to have convection within the core, this liquid core, to generate a magnetic field, or one way to generate a magnetic field. We have convection when we can remove heat quickly from the core. If we couldn't remove heat quickly from the core, we would just remove heat by conduction, but that's not enough to twist these magnetic field lines within the core to generate Earth's magnetic field. So one way to actually ensure that you have convection is to remove heat from the mantle very quickly, and plate tectonics is really good at doing that. So we think that plate tectonics probably took over as the dominant source of cooling the mantle, and hence cooling the core and powering the Earth's magnetic field during this transition period of around 3.4, 3.5 billion years ago. And that's what's shown in the next slide again in number 11. But let's just jump right to number 12 now. Now, what followed that transition, in our view, and I'll just note that what's shown here is plotted. All the colored points are from our laboratory. Some of the ones that are in gray are from other laboratories. What followed after this transition to plate tectonics, or plate tectonics kind of powering the Earth's magnetic field, was a period over 2 billion years long where there were variations in the strength of the magnetic field, but it was continuously becoming weaker and weaker. And we think the reason for this was the fact that this cooling and just removing heat from the core was becoming less and less efficient. That is, the temperature contrast between the core and the mantle was becoming less. It didn't happen overnight. It took 2 billion years, but it became less efficient as a mechanism for driving the magnetic field. And this is really where the discovery part comes in. If we just go to our next slide. What is shown here in, if you can look at the purple, I think it's a hexagon there, you'll see a data point where the field is extremely low. It's actually 10 times weaker than the present Earth's magnetic field. This is almost at the point that the Earth's magnetic field completely collapsed. This is something that was discovered by one of my graduate students. We had some suspicions about this, but we really didn't know that the Earth's magnetic field was that low at that period. And the really neat thing about it is that is a result that was just generated by Richard Bono, who is now an assistant professor at Florida State University. Richard generated these data completely independent from another work, which I'll talk about in the next slide, number 14. And this is the work of Peter Driscoll, who's now at the Carnegie Institute. Now, time in his plot is going the other way. So on the right-hand slide of GA is billions of years ago. So time, the recent, is 0 there on the right-hand scale. But I've highlighted in the pink rectangle 2 of the key predictions. Now, Peter wasn't generating data. Peter had a thermal model of the Earth and a geodynamo, a numerical model of the Earth, and he made a prediction. He made a prediction that right before the inner core started to form, the as I talked about, the energy would have been so low to generate the field that the field would be almost at the point of collapse. But then, as soon as the field started to soon as the inner core started to grow, there would be new energy sources, so the intensity should jump up again. So those were his 2 key predictions. So the first prediction of this really low field was really something that Richard Bono found independently and reported on in 2019. And if we jump to the next slide, in 2015, this is the newest work from our lab, from my student Ting-Hong Zhao. And what Ting-Hong found was essentially data that is the second part of matching the prediction that Peter Driscoll had made. And that is, in the early Cambrian period, there's a rapid recovery of the Earth's field strength. So if we just jump to slide 16, that's the red data square there. So we go from this extremely weak magnetic field where it's almost at the point of collapse and the field jumps up. That time interval is something less than 33 million years. That's a long time for you and I, but in geological terms, that's actually a short period of time. We can expand upon that in the next slide, number 17. And that just kind of shows a blow up of that area now, where since the time of Richard Bono's work and this ultra low field that he recorded in what we call the Ediacaran period, there have been other studies by other groups, those are the smaller data points, that have confirmed his values. And the bottom slide basically shows our view of when the inner core formed. The red line going along the bottom, and then we start to form the inner core, and then it grows in radius, which is the y-axis in part C. So our current view is that the inner core of the Earth formed at around 550 million years ago. Because we know that, now we can actually put a date on. I mentioned that there was an innermost inner core. So the inner core actually has two parts to it. And we think that that transition occurred about 450 million years ago. And we think that that actually reflects a fundamental change in how plate tectonics was working at that time, because that plate tectonics is ultimately causes or what we say controls the ultimate heat that's coming out of the Earth. So there was a change in how the mantle was actually releasing its heat at around 450 million years ago, and that caused a change in the structure of the innermost, between the innermost inner core and the outermost inner core. So in the next slide, this just now brings us all to completion, and that is, since this time interval, the Earth's magnetic field has been dominantly powered by the growth of the inner core. So the inner core has formed, and it is now powering the Earth's magnetic field. But that was not the case for all of Earth's history, or even most of Earth's history. So let's just jump to number 19, slide 19, and really kind of talk about some of the, I think, the larger implications of all this, and part of what drives us toward our research. And let's kind of do this, I think, in an interesting way, and think about kind of alternative Earths without a geodynamo origin and continuity that we're talking about. What's shown in the left is a picture of Earth and Mars, how they might, these are cartoons, of course, how they might have looked at 4.2 billion years ago. So they both have magnetic fields, and they both have oceans. But obviously, the planets have evolved in different ways. Mars lost its ocean, but Earth retained its ocean. So there are two critical points in transitions in Earth history, in our view, that if not leading exactly to a Mars-like state, could have pushed Earth much closer to Mars than its present-day state. The first, which isn't really the topic of this talk, but I have touched on it, is this very earliest Earth, the Hadean to Paleoarchean. So this is the 4.2 to 3.5 billion year period. Solar winds would have been so intense then, if we didn't have a magnetic field, we would have eroded Earth's atmosphere, and we probably would have looked something much more like Mars. But the second one is this Ediacaran period and the inner core growth, because we might not have evolved like Mars, but if the Earth's magnetic field had not regenerated by the formation of the inner core, and I'd like to emphasize that point, because it's very exciting now that people are thinking about exoplanets, and we're in this great point in history where we're making the first discoveries of exoplanets, and everyone's interested in whether or not there are other planets that are habitable. So we need to understand Earth, of course, as that model. So it's not obvious that when you have an inner core that you're going to drive, and inner core formation is automatically going to regenerate the magnetic field. If the chemical composition had been slightly different, if the materials had been slightly different, we might not have regenerated the magnetic field, and we might have gone into a very different state where without a magnetic field, the Earth's atmosphere would have been much more vulnerable to removal. So we would probably in 500 million years not have evolved to Mars, but we would have lost water, and we would have been a much drier planet than we are today. So I think it's kind of interesting to put Earth evolution kind of in that history, that the formation of the inner core really for Earth was an important something very deeper in the Earth, really had fundamental consequences for the surface environment that we know today. So finally, just in number 20, I just like to mention that I'm really just representing a large group of collaborators, and these are just some of the collaborators in some of my most recent studies. They're not all listed here. And of course, we are funded by the National Science Foundation, who kind of enables us to do many of this work. I've talked about a lot of technical things in a very general way here today, and my email address is there. Particularly if any students would like to talk about any of these things in detail, they should feel free to send me an email. So that's the end of my formal presentation, and I'd be happy to take any questions.
Well, thank you so much, John, for this beautiful presentation and for explaining things in a way that even I can understand. So, Leah is asking, what is the difference about the characteristics of the inner core on Earth, that it doesn't melt under the same conditions as the liquid layer around it?
Right. So um, it has to do with the pressure temperature characteristics of Earth. So the when the iron actually starts to crystallize, it actually there's a certain number of light elements in the core, and there's incredible debate in the community, interestingly enough, about what some of those light elements are. Surely there's oxygen, surely there's some um, silica, whether or not there's hydrogen or not is debated. Um, uh, Certainly some magnesium. So what happens is when this material starts to crystallize, these lighter elements are exposed from the liquid. So now the liquid does actually have a different chemical composition from the center of the very center of the core itself. But it really is a pressure temperature um, condition, so that the pressure and temperature characteristics of the overall core become you pass into a we call phase regime, where the solid phase is stable. Okay, so it's really the pressure and temperature characteristics that are really defining where we have a solid phase being stable and versus a liquid phase being stable. Overall, the core had to cool to a temperature low enough that that would start to happen. Okay, I hopefully that's clear.
Yeah, I think that's interesting. And so, why didn't Mars come up with this field? Um, do we know exactly why? Do we know enough about Mars?
We just have some ideas because probably so Mars doesn't have plate tectonics, so it was not releasing heat at the rate that Earth was, so cooling its mantle fast enough or in a way that would kind of generate the field. But also the chemical composition of the core is quite different. There's much more sulfur, we think, in the core of Mars than there is in Earth. So my guess is probably the sulfur is the main difference for this. That you can reach the solid phase within the Martian core, but those chemical characteristics are not enough to create the conditions to release enough heat to generate a magnetic field in Mars.
Interesting. So the proximity to the sun doesn't contribute at all.
No, the proximity of the sun to the sun just has a rough it has a direct correlation on the composition. But beyond that, it's really the intrinsic nature of how the planet was built. So Mars probably was built as a planet very different from Earth. Um, you know, our estimates right now is Mars may have actually consolidated as a planet much earlier than the Earth did. So when we're talking about Mars, we're talking about 5 to 10 million year timescales for after the formation of the solar system. When we talk about Earth, probably like more than 30 million years, and Earth was being built by probably smaller planetesimals. So it had a longer and more protracted growth history, and that all played into the chemical composition that eventually formed its core.
Oh, that's interesting. I didn't know that. Joyce, do you have a question?
Yeah, a couple thoughts, and I'm sorry if I may have missed part of it. So if you said something about this already, but anyway, I'll just ask: do you think there are any implications for one of two things, either our future as far as climate, or finding other planets that are habitable in the solar system, or actually beyond the solar system? Anyway, thanks. I'm done.
Yeah, no, that's a great question. So, I've touched on that a little bit, but not as much as in terms of your first question. So the it does have some implications for the future of our planet, but um, there's going to be a grand competition here. I mean, we can talk about what's going to be the demise of our planet, and I think I is the inner core. Maybe this is a good way to think about it. If there were no other variables involved, the inner core will continue to grow. At some point, and the inner core is going to become so large that the that portion of the core where the Earth's magnetic field is being generated becomes so small that the flow actually starts to break up into smaller areas, and at that point, then the actual potential to generate a global magnetic field becomes questionable. So then the magnetic shielding would essentially collapse, and then we could then have the full brunt of the solar wind impacting the Earth, and then potentially removing the atmosphere and the water. However, that's probably going to be and this is where models will differ on this. 500 million to 1.5 billion years in the future. But at that point, then we start thinking about other things that are going to happen in the solar system that are going to be equally or bad or worse, because the sun is going to start to grow toward a red giant phase, and it's going to cause a runaway greenhouse on Earth, and the surface temperature is going to become uninhabitable. So there are interesting academic questions there, but there's other things as well that go into Earth's future. What I would say, and that's kind of touched on a little bit in the link that I think was posted, is the Earth's magnetic field is really interesting right now, and it's decreasing in intensity, for example. And this has caused a great debate in the community about whether or not we're heading toward a reversal or not. I won't go on record as saying that we're heading toward a reversal. I'll just say that the Earth's magnetic field is decreasing very rapidly, and that does have some concerns for us, some societal concerns if that continues, because it can affect satellite operations, and it could, if it continues in the next 50 years, increase, let's say, concerns about skin cancer, because the Earth's magnetic field also, through its protection of the ozone, eventually protects against UV light. So I think those types of connections are important. In terms of the exoplanet question, yeah, I think this is a prime consideration. I think everything that we've talked about bears on this, that you can think about the creation of a planet in a solar system in what we call a habitable zone. That's the zone where water is actually in the liquid phase. But that's not enough. I mean, you can create a planet there, but you have to find ways of keeping the water on the planet. So again, I would return to what I talked about at the end. I think that's sort of general. I think in all exoplanets, need to that want to have habitable futures as we view them. They have to survive this early phase. All stars or sun-like stars, in their when they're young, throw off a tremendous amount of particles, and when that happens, that has tremendous erosive capability of a early planetary atmosphere. So all planets need to survive that, and a magnetic field is a great way to do that. And then later on in their history, they need to find something in their internal dynamics to create and continue this magnetic field, and the formation of an inner core is one great way to do that, obviously, from the Earth example.
Yes, thank you very much. Yeah, so it sounds like we're going to be very lucky if we have to worry about that, because it'll mean
Yes.
we made it for 500 million years.
Yep. Yep.
Okay, thanks so much. I'm
Sure.
done.
Yeah, there were more questions just posted. The Venus does not have a magnetic field, and if that's true, how can Venus keep up the atmosphere?
Yeah. That's a great question. So Venus is our classic example of a planet without a magnetic field. So the question is, well, if magnetic fields are important, why does Venus have such a thick atmosphere? And the question there, of course, is not the preservation of an atmosphere or per se. It's the preservation of a habitable atmosphere, a habitable planet. Venus is hell, right? Venus has lost all its water. So Venus has this crushing CO2 atmosphere. It has sulfuric acid clouds, and the reason for this is it hasn't released its heat in sort of a normal Earth-like fashion. It releases it sort of in events, but for at least for the last 800 million years or so, it has lost all its water. And it lost all its water probably in part because it didn't have a magnetic field to actually prevent that from happening. So it is a good point that we're not talking about the preservation of atmospheres. We're talking about the preservation of water and habitable atmospheres by a magnetic field. And of course, when you're thinking about the removal of elements, the easiest thing to remove is going to be hydrogen. And it's really the breakdown of water and the removal of hydrogen that is the start of that process in removing water. And you know that's actually still happening today in Venus. We can actually record it by satellites. The second part is a little bit more nuanced. And it's not just these parameters, but once you remove all the water from a planet and you're just left with CO2, there's actually something we call an adiabatic, that's a technical term, but there's a process by which when you have CO2 at the very feather edge of your atmosphere, when you're actually removing some of that CO2, there's a relative cooling effect. So if we were to look at the feather edge of our atmosphere today, okay, Earth's atmosphere is actually more vulnerable to loss just by the basis of that temperature than Venus is. And that's because Venus has this CO2 atmosphere all the way up to that point. So there's interesting chemistry that happens once you remove all the water from an atmosphere, and in particularly when you're all that's left is CO2.
That's really interesting. I didn't know that there was basically CO2 only left. Like, Do you think for for life, do you think at any point it was possible to have had life on Mars or any of the other planets um, without the magnetic field?
Um, well, one could argue. I mean, Mars had a magnetic field early on. So the question is, would you actually have enough conditions on some place like Mars, um, and long enough time that you would not have eroded away the atmosphere? And it's possible on a Mars-like planet that you could do that, but then you'd eventually remove all the water. So I don't think the sustainability of habitability bodes very well for long-lived life. I do think it is possible, however, just to kind of probe your question, I think it's theoretically possible to have such a thick atmosphere to begin with that it takes time to erode it away, and you could potentially have conditions suitable for the origin of life, but then that life might not survive.
Oh, and Namano, he asked if Aria Borealis, would it be affected if the magnetic field changes soon in the future?
Um, yeah. So the what we think is going to happen. There are some predictions, and I believe those. So let me just back up for a second. What's happening to the Earth's magnetic field is the Earth's magnetic field is decreasing in intensity. That's the overall intensity of the magnetic field, but it's not happening the same everywhere. It's actually decreasing more rapidly in an area called the South Atlantic anomaly. So this is broad area from South Africa over to Chile, and it encompasses part of Brazil, where the Earth's magnetic field is much lower um, than typical for the field strength that should be. So it's actually and it has some spatial characteristics to it. Now, if that continues to weaken and continues to grow, Earth overall is more susceptible to having, when there's very large events from the sun, these coronal mass ejections impacting the Earth's magnetosphere. Now, what happens there is then there's a transfer of some of those particles. They don't reach Earth's surface, but there's a transfer of some of those particles to the radiation belts that surround Earth. These are called the Van Allen radiation belts. And then they can actually spark off auroras. So I think that if the Earth's magnetic field continues to decrease, an argument could be made that you could have more frequent occurrences of auroras at lower latitudes. So I think that would be the main connection.
Oh, interesting. Yeah, thank you. Does anyone have any last questions? We have around 5 minutes left, and the hour is up, and John probably has to get back to work and life. So, yeah, if anyone has any last questions, please go ahead and ask them now. So, my question is also, what would the outcome, like, what would change for the ocean and ocean currents? Would there also be maybe, would it be affected, like, for ocean life and currents, because then that changes the climate probably also a lot? Or is it maybe, climate change is way stronger effect and it won't really make a difference?
Yeah, I think climate change is kind of is the larger effect in general. Anthropogenic climate change. Climate really doesn't come into this until you get to the really drastic situations where you're, removing a large part of an atmosphere or something like that. Kind of on the more general cases, I think climate really isn't affected. I mean, there is still some argument in the discipline about whether or not the magnetic shielding of cosmic rays could have some local effects on climate, but it's there's nothing of the scale of the larger signal of anthropogenic climate change.
Yeah, and I don't know if you like the birds and so on are theorized to use the magnetic field for orientation.
Well, that's actually another question and a fascinating one, and yeah. So if we were to ever to go to the case where the Earth's magnetic field were to really continue to move toward reversal, and again, not something we need to worry about, because if that were to happen, that would be probably at least 1,000 years into the future, maybe 1,500 years into the future. I think the field might start to get very unusual around 500 million years, if there were, let's say, a linear continuation of the trend that's happening and over the last 200 years, which is an unreasonable extrapolation, but nonetheless, for fun, we could talk about that. But I think that it is an interesting case, because there does seem to be strong evidence that certain animals do use the Earth's magnetic field for navigation. However, I think for many of these groups, it's also clear that they use multiple sensing organisms to actually do this process. So I don't think why there might be local effects. I don't think there's going to be mass extinctions that would result for this, because like birds, they clearly have multiple sensors, and they're sensing different parts of the electromagnetic spectrum that we can't see um, for this type of navigation.
Interesting, and by then we managed to kill all of them, probably.
Yeah, yeah, yeah.
Except those zoo, if there's still a zoo, so they don't have to navigate. Yeah. Does anyone have any last questions? Please feel free to post them here. So I know you kind of also changed the notion of tectonic plates, movements, and so on. So in practicality, how do you get the data? So you have different spots around the world where you continuously get still data from to update your model. Like, is that like how large is the network basically to make like these type, to get this type of data that you can make like a model out of it?
Yeah, so there are two different things. There is one is that there's what we call a paleomagnetic database. So there's data from rocks all over the world that we can continue to contribute to. And right now, as I said, we're focusing on the strength in the magnetic field. But our contributions have mainly been from the oceans. I mean, one of the problems in those so-called global databases is that they're almost entirely from the continents, because it's really hard to get data from the oceans. So that was some of the work that we did with the ocean drilling program, and particularly in the Pacific, because the Pacific plate, the huge Pacific plate, is a key player there. So we led some expeditions drilling seamounts on the Pacific plate, and we drilled through those, and we examined other data that had been collected from previous missions to get paleomagnetic data to make conclusions on really not only what the plate was doing, but also making inferences on what the mantle was doing, and kind of our view that I think changed a lot of people's mind was that it's not just all the plates that are moving, but the mantle is moving, and sometimes the mantle can move as fast as the plates. So, and not necessarily in the same direction. So I think that the Earth and the mantle is convecting. The Earth is a huge convecting system, and actually taking into consideration all parts of that system is really important in figuring out, how the Earth works.
Can I that's really interesting. And can I make a type of sci-fi since we are on Clubhouse, and you know not everything has to be formal. So
Yeah.
will there ever be a tunnel that goes really deep, maybe deep enough to get some there's this sci-fi movie where there's a tunnel between, I think, the US and Australia, that you're there in like half an hour. So people work like in Australia and live in the US or something like that. I forgot exactly. It's a while ago. Like it's probably not possible, right? And it would
Yeah.
probably collapse and get way too hot. Like how hot would it get when you
It gets really hot really pretty quickly. So let me put this in perspective to you. I talked about the mantle. Um, so the Ocean Drilling Project has been trying for 50 years to drill in the ocean basins through the oceanic crust. That's the uppermost part of this uppermost layer called the lithosphere, to get into the mantle, because that's the easiest place to reach it. Now, it turns out that there are other places where the mantle is on the surface of Earth, but they're all special because there's some kind of unusual tectonics and some type of deformation that's brought these rocks from these incredible depths to the surface. What people really want to do is look at like kind of in situ material to see what that mantle really is like. So they would like to drill through the entire crust to get to it. We tried for 50 years and we haven't been able to do it. So drilling through the oceanic crust is really, really hard, and and it gets hot, and there's all sorts of technical problems. There are voids that are terrible if you're trying to drill. It's fractured, and it's so. If we could actually drill into the mantle, I'd be happy. But I think the science fiction movies are that they're science fiction. They're cool and they're interesting, but they're very far from science in that aspect. I do think we will eventually. I mean, there are large scientific groups out in Japan and the U.S. who want to do this, but it's still a major technical challenge to get just to the very top of the mantle.
Wow, interesting. I didn't know. So it's extra hard, the surface, or is it the
Yeah,
pressure in
temperature, pressure, but really structure also. So
okay.
it's yeah.
Well, interesting. So I could fantasize way more going into on how to get into the earth and what's under there. I had one more question. There's a lot of talk of having another ocean under the surface. Is that something we really know? Like, did we manage to really detect it, or is it a theory that we have a whole other ocean under the ocean, basically, or under the surface?
We don't really have another ocean in the sense that you would think necessarily of an ocean. We have many, many different types of reservoirs on land, and there are undiscovered reservoirs on land, probably, where there is sort of untapped deeper water, but not ocean scales. There could be some large water bodies, but not anything the size of an ocean. Now, there will sometimes people will talk about this and say, well, there's ocean in the mantle, and particularly there's ocean in the deep mantle. Well, what they're talking about there is that there is water trapped in minerals, and if you could release all that water, you would get some fraction of an ocean. And we don't actually know those numbers, but that is actually certainly true. There's a significant amount of water that is trapped in minerals in the mantle, and maybe even the deepest mantle, and and that's part of our water budget too, from the entire planet. But there's great debate in the community as to how much water that is.
Oh, that's interesting. And would it be salty also, since it's trapped in minerals, or is it just different, just magnesium and stuff like that?
Well, it definitely would be. It would be. It would have many minerals in it because it's actually bound within those minerals. Yeah, so it would be. It wouldn't be fresh water.
It wouldn't be okay. So let's just leave it there. We have enough salt water soon coming to our
Yeah.
eating away at the beach and stuff. So maybe we should just keep it there.
Yeah.
Yeah, great. This is such a wonderful discussion. I could go on and on talking about my curiosity. Um, but I would like to, let you go on with your day and your Friday. So it was really an honor having you here, and you're always invited back. And this was such a pleasure. I hope you enjoyed it too. And yeah, thank you so much.
Okay. Well. Yeah. Thanks for inviting me, and I did enjoy it, and thank you again.
Wonderful. And yeah, thank you everyone for coming, for asking questions in the chat and participating, being here. If you like discussions like this, follow the club. We will have next week more discussions like this. Check out the club website or the schedule. And yeah, I hope to hear you all back soon. And thank you, John. It was such a pleasure. Enjoy your weekend. Thank you.
Okay. You also. Bye.
Bye. Close the room in 3, 2, 1. Bye, everyone. Thank you.